ABCD is a square with side length equals to 2. M is the midpoint of the side AB, and N is the midpoint of the side AD. Construct the red side MN. Let's take it as a diameter and draw a semicircle. We also take the green side CD and do the same thing. The two semicircles intersect at the points E and F. Draw the sides to form a quadrilateral. Find the area of CDEF. There are two major directions to approach this problem. The first one is coordinate geometry. We're going to figure out the exact positions of E and F, that is, their coordinates. The second one is deductive geometry, that is, to find the lengths of all the sides of CDEF. We shall come back to this planning from time to time, as you will see how different branches of math come into play. Alright, let's start with the first direction. We introduce a rectangular coordinate system such that the positive x-axis is DC and the positive y-axis is DA. Therefore, point D is the origin. Now, we call the largest semicircle C1 and the smaller one as C2. Their centers are P and Q respectively. Next, we are going to give the coordinates of the points. Because the side length of square is 2, so let point A be 0, 2, point B be 2, 2, and point C be 2, 0. Moreover, because M is the midpoint of AB, so the coordinates are 1, 2. Likewise, the point N is 0, 1. Then we can move on to the two semicircles. Here, the center P is equal to 1, 0. For the center Q, it is the midpoint of diameter MN. Therefore, the coordinates are the averages of M and N, which are 1 over 2, 3 over 2. How about the radius? For the green semicircle, it is obviously 1. For the red one, the radius is equal to 1 over 2 times the diameter MN. We apply the distance formula. Therefore, the radius is equal to 1 over square root 2. Alright, everything is ready. We can figure out the equations of the semicircles. For C1, it is x minus 1 whole square plus y minus 0 whole square is equal to 1 square. Expanded and simplify, we have x squared plus y squared minus 2x is equal to 0. We call this equation 1. When it comes to C2, the equation is x minus 1 over 2 whole square plus y minus 3 over 2 whole square is equal to 1 over square root 2 whole square. After some simplification, we can get rid of the fractions and surds. So it is x squared plus y squared minus x minus 3y plus 2 is equal to 0. We call this equation 2. Now, what can we do with these two equations? Let's subtract equation 2 by equation 1. So the x squared terms and y squared terms are cancelled out. The remaining are linear terms and constants. So the equation becomes x minus 3y plus 2 is equal to 0. Actually, it is the equation of this purple line. Why is it the case? Because solving the simultaneous equations means that we find the points of intersection. In other words, it is the equation of the chord EF. Now, we make x as the subject and call this equation 3. We can put it into equation 1 to eliminate the unknown x. It becomes a quadratic equation in y, so it gives the y coordinates of both E and F. If you want to go over the expansion and simplification, just pause the video for a moment. The simplest equation is 5y squared minus 9y plus 4 is equal to 0. Now, we can factorize the left-hand side easily. So we get y is equal to 4 over 5 or y is equal to 1. Put these values back to equation 3 to solve for x. When y is equal to 4 over 5, x is equal to 2 over 5. That's the coordinates of E. When y is equal to 1, x is equal to 1, and that's for the point F. So we'll have the coordinates of both. Great! The positions of the 2 points are solved by equations of circles. How to find the area of CDEF? This is not a very nice quadrilateral. Here we use two different methods. The first way is to cut it into three parts, while the second way is the so-called Shoelace Formula. Let's start with the cutting method. Now, we draw the two vertical lines from E and F. Here we use three different colors for the regions. The two lines intersect the x-axis at the points S and P. Just a moment. Is this P the center of the largest semicircle? Yes, it is. You see, F is equal to 1, 1 and P is equal to 1, 0. Because they have the same x-coordinate, that's why they lie on the same vertical line. This special result is a useful insight when we talk about the second approach by geometry. Let's work out the area of each part one by one. For the green triangle on the left, we have S is equal to 2 over 5, 0. It is because it has the same x-coordinate as the point E above, and the height is clearly 4 over 5. So the area is equal to 1 over 2 times the base 2 over 5 times the height 4 over 5, which is equal to 4 over 25. For the purple triangle on the right, it is even simpler. Both the base and the height are 1, so the area of triangle is equal to 1 over 2. Now, we come to the blue trapezium at the middle. The upper side and the lower side are 4 over 5 and 1 respectively. The height of the trapezium is this portion SP, which is equal to 3 over 5. Therefore, the area of the blue part is equal to 1 over 2 times the sum of upper and lower sides times the height 3 over 5. It is equal to 27 over 50. Now, the area of CDEF is the sum of these three parts, which is equal to 6 over 5. Well, I guess you are not quite satisfied with this method, right? It just takes too long to arrive at the answer. How about the second method? That is the Shoelace Formula. It's actually two columns of coordinates like this, with an extra 1 over 2 outside. How to write down this formula? We start from the origin D with coordinates 0, 0. Now, we move on to the point C, which is 2, 0, point F, which is 1, 1, and point E, which is 2 over 5, 4 over 5. Finally, we go back to the origin. We have walked around the polygon in an anti-clockwise direction. Well, the formula doesn't look like a matrix nor determinant. So, what's that? Indeed, this is a notation for the following computation. Referring to the green arrows, we multiply the terms like this, and then add them up. Next, we do the same for the blue arrows. They are in another direction, so we put a negative sign in the front. Does it look like a shoelace? Because there are so many zeros, we can get the answer in a much more effective way. Of course, the area of CDEF is equal to 6 over 5. Alright, can we do it in an even better way? You see, the coordinates of E and F do not involve any square roots. Indeed, F is equal to 1, 1. It suggests that F is the center of square. Is there any geometric significance? The next thing we are going to do is to prove this without using equations of circles. We let the center be G1, 1. It is clear that the length GP is equal to 1, which is equal to the radius of C1. So G lies on the green semicircle. At the same time, because we have a right angle here, therefore MN is the diameter of the circle passing through M, G, and N. The reason is converse of angle in semicircle. In other words, G lies on C2. Altogether, we can say that the two semicircles intersect at the center of square. Our next question is, what about the point E? Let's put aside the two semicircles for a moment. Construct the two line segments DM and CN. You might say, there's nothing to do with the point E. Give me a second. I'm going to show you some surprising results. Now, we look at the red triangle MAD and the green triangle NDC. Because they are overlapping, let's separate it into two figures like this. What can we say about them? Well, they look alike. So we're going to prove that they're congruent. clearly we have two pairs of equal sides. They are MA is equal to ND, which is equal to 1, and AD is equal to DC, which is equal to 2. We also have these two right angles. Therefore, the two triangles are congruent, and the reason is SAS. So what important results do we have? You see, these two angles are corresponding angles. Let's call them theta. Then, by angle sum of triangle, this angle at the point D is 90 degrees minus theta. Now, we can combine these two figures together like this. Name this point as H. We're going to show that the two semicircles also intersect at this point. Let's focus on this blue triangle. By exterior angle of triangle, this blue angle is 90 degrees. It is a crucial link between triangles and circle. Therefore, we can say that DC is the diameter of the circle passing through D, H, and C. The reason is, again, converse of angle in semicircle. Let's look at the upper part. Now, this red angle is also 90 degrees because of vertically opposite angles. Likewise, we have MN being a diameter of the circle passing through M, H, and N with exactly the same reason. So the two semicircles intersect at the point H. This helps a great deal in solving the coordinates of E. At this moment, we also have two branches to solve it. The first one is equations of straight lines, and the second one is by vectors. Let's start with the first method. For the red line DM, we have the coordinates of 2 points. So the equation is y minus 0 over x minus 0 is equal to 2 minus 0 over 1 minus 0. We have y is equal to 2x. Let's call this equation 3. Next, for the equation of the green line CN, we can do exactly the same thing. In this case, we have y is equal to negative 1 over 2x plus 1. We call this equation 4. It is much easier to solve these two equations. We put equation 3 into equation 4 to get rid of the unknown y. After solving, we have x is equal to 2 over 5. Put this back into equation 3, then y is equal to 4 over 5. So E is equal to 2 over 5, 4 over 5. We get exactly the same result as in the previous part. Now, let's move on to the method by vectors. Go back to the coordinate plane, we let vector DC equals to 2i and vector dn equals to j. Therefore, the blue vector dm is equal to I plus 2j. Now, consider the point E again. We let NE to EC is equal to 1 to k. Then the vector DE is equal to vector DC plus k times vector dn over 1 plus k, which is equal to 2i plus kj over 1 plus k. This is the section formula in vectors. To solve for the value of k, we make use of the fact that vector DE is parallel to vector DM. Therefore, we have equal ratio of coefficients. 2 over 1 plus k divided by 1 is equal to k over 1 plus k divided by 2. Cancel out the denominator 1 plus k on both sides, we get k is equal to 4. Put this back into vector DE. Then it becomes 2 over 5i plus 4 over 5j. We get both coordinates of E at the same time. What about the area? For each of these two methods, we can use either cutting the polygon or the Shoelace formula as discussed before. So we have 6 different branches in coordinate geometry. What about the deductive geometry approach? We are going to figure out the lengths of the line segments, DE and EF. Let's call them A and B. We put aside the two semicircles for a while and focus on the red triangle MAD and the blue triangle NED. Again, we separate them into two figures like this. Indeed, there are 3 pairs of equal corresponding angles. The first pair is a common angle at the point D. Another pair is these two angles, which are theta. The third pair of angles are both 90 degrees. Here, the blue right angle is proved already in previous part. Therefore, the two triangles are similar, and the reason is AAA. This result helps us solve the length of DE. Before that, we need one more length. Here, the hypotenuse dm can be found by Pythagoras' theorem. So, dm is equal to square root 5. Let's check two pairs of corresponding sides. The first pair is dE over dA, and the second pair is the hypotenuses dn over dm. We put the lengths inside. Therefore, A is equal to 2 over square root 5. Let's go back to the overall picture. We got the value of A by similar triangles. What about the length B? We have another two ways to solve it. They are Cosine Formula and Ptolemy's Theorem. Let's look at the first one. We jump back to the original figure. Now, this angle at point C is 45 degrees. Still remember point F is the center of square? So it is the properties of square. From this, we can talk about the angle at point E. If we just look at the green semicircle, you can see that CDEF is a cyclic quadrilateral. Because the two angles are opposite angles, so their sum is equal to 180 degrees. That is, the angle at point E is equal to 135 degrees. That's about the angles. Let's move on to the sides. Construct the diagonal BD. Again, the length can be found easily by Pythagoras' theorem. That is, dB is equal to 2 times square root 2. By properties of square, dF is equal to half of dB, which is equal to square root 2. Likewise, CF is also equal to square root 2. We're going to use this result later. Now, the side DF divides the polygon into two parts. For the upper triangle, we have three sides plus an angle. Then we're going to use the cosine formula, which is a squared plus b squared minus 2ab cosine 135 degrees is equal to square root 2 whole square. We put a equals to 2 over square root 5 into the equation and simplified it. Now it is a quadratic equation in b, which is 5b squared plus 2b times square root 10 minus 6 is equal to 0. It is not straightforward to factorize it. However, we can apply the quadratic formula to solve for the exact value of b. Let's simplify the expression. The second surd is equal to square root of 160, which is equal to 4 times square root 10. Therefore, b is equal to 2 times square root 10 over 10, or negative 6 times square root 10 over 10, which is clearly rejected. So b is equal to square root 10 over 5. Using cosine formula is quite complicated. Let's see how to apply the powerful Ptolemy's theorem to find the value of b. Here we need another diagonal. Let it be small letter c. We look at this blue triangle. Then this angle at point E is equal to 90 degrees because of angle in semicircle. Then we can apply Pythagoras' theorem. That is, a squared plus c squared is equal to 2 squared. After solving, we have c is equal to 4 over square root 5. So how do we use Ptolemy's theorem? Now, the product of the two green opposite sides a times square root 2 plus the product of the two red opposite sides 2 times b is equal to the product of the two diagonals c times square root 2. Divide both sides by square root 2, we have a plus b root 2 is equal to c. Putting the values of a and c inside, we get b equals to square root 10 over 5 again. Alright, all the lengths are determined. Now we can consider the area of CDEF. We divide the polygon into two parts, and it is the same for each branch. Let's work out the area of the green triangle first. It is equal to 1 over 2ab sine 135 degrees. We put the values of a and b inside and simplified it. So the area is equal to 1 over 5. For the purple one, it is a right-angled triangle by properties of square. So the area is simply 1 over 2 times square root 2 times square root 2, which is equal to 1. Therefore, we get the area of CDEF, which is the sum of these two parts. Again, it is equal to 6 over 5. It's so amazing to combine different branches of math in problem solving. You don't want to miss this classical problem, which includes 9 approaches from geometry to trigonometry, from matrix to complex numbers. I will see you there.